Welcome back to our lecture series in DC machines and transformers. In last class we were discussing about commutation, ideal commutation, what is the process of commutation, how the current reversal happens, and finally we got a curve like this where this was our case 1 where current in coil A was 20 ampere. I hope you remember where the brush was placed in this condition. The brush will be placed in such a position, in this position, because we are having 20 ampere from left side and 20 ampere from right side. Both the 20 ampere will meet here, because one and only path for the current to go outside is this brush. So that there is no path through this connection, no path through this connection, because this is insulation. The red color marking is insulation. So all the current have to follow this direction. So that what happened? 20 ampere will come up to this point and this 20 ampere will come up to this point and they will meet at this point, and total 40 ampere will pass through the brush to the output circuit, outside circuit, external circuit. So that this is the brush. And the current in the coil A is plus 20. This is the positive direction. These things are already explained in the previous class. If you are having any doubt, this should be very clear for you for understanding today's class. Otherwise, you will not get any idea about the practical difficulties of commutation. First of all, you have to learn ideal commutation. Then only you can understand the delayed commutation. So, in today's class, we are discussing about delayed commutation. Delayed commutation. So, please go through the previous lecture if you are having any doubts regarding the ideal commutation. So, this was the case 1 where we are having 20 ampere in the coil A. Then we will move the brush a little towards the brush, towards the segment 2. Actually, no, we are not moving brush, we are moving the commutator. But for understanding, I will tell that you will move the brush. Ideally, what you are moving? You are moving the rotor, brush is stationary. Anyhow, the rotor is moved a little bit towards the right side. What happened? The brush will come in contact to segment 2. Both 1 and 2 will come into the contact with the brush, so that some current will pass through this path. So, after some time, you will get 10 ampere through the brush, through the coil 1. Then you will move the rotor again into the right side, so that the brush will be in 50% contact like this, in such a position. Brush will move to such a position, so that coil A will get 0 ampere. Then you will move more towards the right side. You will move the rotor more towards the right side, so that you will get minus 10 ampere. And finally what happens? Finally, 1 minute. And finally, you will reach in this position. Finally, you will reach in such a position that the brush is only contacting the segment 2 like this. No contact with segment 1. This is the last position where we will get minus 20 ampere. Can you explain that? How we are getting minus 20 ampere? Can you explain this? Because now the current is having only one and only path, that is through this connection. Because this side it is isolated. No way to pass to the brush. This is in contact with brush 2 and the insulator. So, current from the left side will come up to this point, that is 20 ampere, and current from the right side will come up to this ampere, and the total current 40 ampere will pass through the brush. This is the things up to this we explained in the last class. Anyhow, we need this case for explaining delayed commutation. So, coil A is carrying 20 ampere in the opposite direction as compared to first case. So, that is minus 20 ampere. So, this is the case. You please clear your concept in the ideal commutation initially. So we will get such a characteristics. This is also obtained in the last class. Now what is delayed commutation? Ideal commutation is over. I just brush up those things for getting for having better understanding. Now what is delayed commutation? That is another thing. Before going into that, you have to brush up the concept of an inductor. Actually, what is the windings? Windings are inductors. Inductors are having a property self-inductance. Inductors are having a property self-inductance L. That is, whenever current is changing, it will produce some EMF. That EMF E is equal to L di by dt. EMF produced by an inductor E is equal to L di by dt, and L is self-inductance. That is property of inductor. If current changes suddenly inside an inductor, it will produce an EMF. Whenever current is changing suddenly, it will produce an EMF. So that EMF is known as self-induced EMF inside an inductor. Actually, what is commutation? Commutation is a process of reversal of current inside a coil which crosses the brush axis. If in this case brush A is that particular coil, and inside the coil A, what is happening? You can see the current is, initially it was plus 20, then 10, then 0, minus 20, minus 10, minus 20. So current is suddenly changing inside this coil A, and this coil A is an inductor. So what happened? An EMF is induced inside that coil. So this is the point. In any coil, if there happens a sudden change in current, an EMF is induced. Self-induced EMF is induced. So in this case, what is DI? Current is changing from plus 20 to minus 20. So what is the change in current? 20 minus 20. 40 ampere is the change in current. And what is the time dt? This is the time where the change happens. This is the small time. This is di, and dt is Tc or commutation period. This is dt. So clearly we can see this equation is very relevant in this case, because di by dt happens and the coil is having an inductance L. Then suddenly we will get an EMF. So this is your point. Whenever a coil undergoes commutation, it will produce an EMF inside that coil, and that EMF is known as reactance EMF. Very important point. That EMF is known as reactance EMF, ER. Generally you can write small letter E. ER is equal to L di by dt, where dt is commutation period. Now what is the issue? Okay, that you have a EMF. What is the issue? Do you have any problem with this EMF? Yes, because according to Lenz's law, you have to write in your notebook. According to Lenz's law, this EMF will oppose the cause that producing it. Here, what is the cause? What is the cause for the production of this EMF? Cause is the reversal of current, this change in current, so that this EMF will oppose the change in current. So due to that opposal of the reactance EMF, this straight line will not be a straight line anymore. This will become a small curve like this. You can draw like this. Don't use scale. A small curve like this, so that the commutation period is increased. This is the new commutation period. Due to the oppose, please write in the notebook. Due to the oppose created by the reactance EMF, commutation period increases, and this process is known as delayed commutation. Delayed commutation. You have to write all these things: self-induced EMF, this equation, this thing, and you have to write the definition, like due to the opposition created by the reactance EMF, the time taken for the commutation will increase, and that is known as delayed commutation. Now, what is the practical issue? You please finish these things. Now, what is the practical issue due to the new wave shape or new commutation period? What is the practical issue? Because you are expecting such a commutation and you are moving the rotor in such a speed, but the things are not like that. You are thinking that the current is minus 20 ampere here, but please check, is it minus 20 ampere at this point? Take this as an axis. At this point, this is the time axis. At this point, previously it was 0, but now it is not 0. At this point, previously it was minus 10, but now it is some minus 2 or 3. And at this point, previously the current was minus 20, but now it is some very close to minus 10 ampere. You can see the difference. So that now practically this coil is no more carrying 20 ampere. It is just carrying a current of, you can see, suppose this is 9 ampere. This is 9 ampere, minus 9 ampere at this point. Only 9 ampere is having in this coil A. But is there any other way for the remaining? Actually 20 ampere was coming, but only 9 ampere is permitted to pass through the coil A due to the delayed commutation. Then what about the remaining 11 ampere? That 11 ampere, that 11 ampere will try to flow through this path. Is there any path? No. 9 ampere, okay, this 9 ampere will meet with this 20 ampere, so that this will be 29 ampere, and this 29 ampere will pass through the brush. But what about the remaining 11 ampere? Will it stand still? No. It will try to jump from this commutator segment to the brush through the air. How current can jump through the air? That is known as spark. It will create some high temperature ionized path, and some spark happens due to the ionization, and this spark will create some damage to the brush. So spark will be created. Spark is created, and this spark will damage our brush. This is the issues, or this is the effects of delayed commutation. So the case, initially you should know what was the case where ideal commutation is happening in case 5. This is the case 5. This is case 1, case 2, case 3, case 4, case 5. So initially you have to draw the original figure of case 5 with ideal commutation. Then you have to draw this new cara of delayed commutation, and at this point, correspondingly at this time, check what is the current in the new curve. It is somewhat close to 9 ampere. So the coil A is carrying 9 ampere. Previously it was 20 ampere, but now it is just 9 ampere. So what about the remaining 11 ampere? That will jump as spark. So this is the issue. So what is the basic reason for having delayed commutation? That is reactance EMF. Reactance EMF will create delayed commutation. Due to delayed commutation, some spark happens inside the machine. This spark will damages your brush. So this is the concept of delayed commutation. Now I want to explain what is the remedies. We have to improve our commutation, otherwise our machine will get damaged, our brushes will get damaged. So that we have to improve the commutation, so that we have to adopt some new methods to improve commutation. That method is known as EMF commutation, that we will discuss in next slide. Now we are discussing about a method by using that we can improve our commutation. So in the last section we discussed that there is an issue of delayed commutation, and that issue is mainly caused by what was the element that is creating the delayed commutation, or what is the element that causing the commutation to happen in a larger time? Yes, that is reactance voltage. So we want to cancel the reactance voltage. That is the one and only method. We want to cancel the reactance voltage. Okay. So for that you have to think that you have to cancel some voltage, or you have to cancel some EMF, or you want to neutralize some EMF. Inside a generator there is some extra EMF that we didn't require. So you want to cancel that. For that we are using a new method known as EMF commutation. EMF commutation. And there is not only one single method, there are numerous methods comes under EMF commutation. But in our syllabus we are covering only one method, that is by using interpoles. So under this heading of EMF commutation there are 2 or 3 methods, but in our syllabus, in our time constraint, we are discussing only one method by using interpoles, and this method is really common in all DC generators. In many of the DC generators we can see some interpoles. What is interpole? Interpole or comb pole, it is small pole. Interpole or comb poles. Comb poles or interpoles, they are very small poles. They are very small poles. Okay, we will draw a detailed drawing of the machine with interpole later. Now let me discuss what is the role of interpole. Why we are using these interpoles. Okay, you can read this. Current in the field winding of interpole should be so selected that the flux produced by the interpole should cancel the effect of armature reaction. Or we can write here armature reaction or reactance EMF. For better understanding, I think you can cancel this word, because there is a cross relation between armature reaction and reactance EMF. It is there, but for making it more simple I am not going to that extent. Actually the reactance voltage, there is armature reaction is also having an effect in producing reactance voltage. You just understand this. If armature reaction is not there, this issue will not come. Delayed commutation will not come. At least you have to keep that point in your mind. If armature reaction is not there, or the demagnetizing or cross magnetizing effect is perfectly cancelled, then reactance EMF will not come into picture. Okay. So for the time being you can think like that. The interpole should cancel the reactance EMF. So the flux produced by interpole will cancel the effect of reactance EMF. In a generator, what is the role of flux? Flux will produce some EMF. When the generator is rotating, the flux will produce some EMF. Okay, is that clear? Yeah. So you are giving some additional flux by using interpoles, so that these additional flux should produce some EMF. Flux given inside a generator means when cutting happens you will get some EMF. This EMF will be so selected, or the direction of flux will be so selected that this EMF will be exactly equivalent opposite. This EMF produced by the interpoles should be equal and opposite. Equal and opposite to the reactance EMF. Why so? What is the importance of this term? What is the importance of this term equal and opposite? If it is equal, the magnitude of reactance voltage ER should be equal to the EMF produced by interpoles. EMF produced by interpoles. This should be equal in magnitude and its direction should be just opposite. Then what happens? It will cancels. It will cancels. If it is cancelled, now reactance EMF is 0 inside the machine. Reactance EMF is 0 means there is nothing is present in the machine to delay your commutation. If reactance EMF is there, what happened? Commutation will get delayed. But if reactance EMF is exactly cancelled, no reactance EMF is present, so that your commutation will be ideal, perfect commutation. That is the point. So, what is the thing? Initially, what is the thing? You have to create some interpoles. Interpoles are the small poles and its flux should be so selected that the flux should cancel the effect of reactance EMF. Okay. Now, this is my question. How we can select that flux? Direction of flux. Direction of flux is determined by direction of current is given. If current is going like this, the thumb direction will be flux. If current is going in the opposite direction in the winding, then flux will be moving towards downside. This is right hand thumb rule. Current and flux. I hope you know this. So, if this is the current, flux will be like this. Like that, the current direction should be so selected that the flux direction should be in according that you should able to generate some EMF. That EMF should be equal and opposite the reactance EMF. So, you have to select the direction of current in the field winding. Then you will get the appropriate flux direction and the magnitude will be also adjusted so that this condition should be satisfied. This should be equal. If your EMF will be larger, then what happen? It will create some opposite effect, adverse effect. So, its magnitude is very important. So, the current direction, flux, magnitude of flux, everything is important so that this condition should satisfy. That is the important point. Okay, now I will draw the arrangement of interpoles so that you will get some clear idea. Now, what is the interpole? How you can define an interpole? So, in the previous slide, I explained what is the role of interpole. Now, let me define interpole in some good, a nice definition, and I will show the position of interpole in this drawing. So, in this drawing, you can see it is a two-pole machine. One north pole is here, one south pole is here, and the direction of rotation of rotor is given in the clockwise direction. Okay, so this generator is rotating in clockwise direction. Now, what is interpole? Interpoles are, you have to write like that. Interpoles are small poles fixed to the yoke, spaced in midway between main poles. So, this is the yoke. Actually, yoke is here. You know that if you are completing the figure, it will be looking like this. So, this is the yoke. The outer covering is the yoke. I know the drawing is not that much perfect. Please excuse me. Okay. So, the main poles are already fixed on yoke. Now it is your time to fix the interpoles. So interpoles should be spaced in between the main poles. So in midway, this is the total distance between the main poles. So this is the midway. There is one more importance for this question, that is, this is the geometrical neutral axis. So you are spacing the interpoles in the neutral axis, or you can tell like this also, spaced in the midway between the main poles. Okay. So as it is a two pole system, you should also have two interpoles. If it is a four main pole system, you will get four interpoles like that. So you place the interpoles and fixed it to the yoke. This is the definition about the position. Now I will define the direction. The direction of you have to write, the direction of interpole is so selected that, the direction of interpole is so selected that its direction will be same as the direction of main pole ahead. Direction will be same as the, not direction, polarity, that is the better word. Polarity will be same as the polarity of main pole ahead, polarity of main pole ahead in the direction of rotation. Direction of rotation. Now please tell me, this is the direction of rotation. So what will be the polarity of this interpole? Polarity of interpole, you have to write that polarity of interpole will be same as that of polarity of main pole ahead. This is the main pole ahead. If this is the interpole you are considering, this is the main pole ahead. How you can comment about the ahead or behind? You have to check the direction of rotation. This is the direction of rotation of rotor. So if you are rotating like this, for this interpole, this is the main pole ahead. So direction of this interpole will be same as the ahead main pole. So this will be south. And what about this one? The rotor is rotating in this direction. So its direction will be same as the direction of main pole ahead in the direction of rotation. So this will be north. Okay. Now the things are very clear. So after, if it is a conductor, if the conductor passes this north pole, it will be having some reactance EMF inside, and that reactance EMF will be cancelled by this upcoming south pole, like that. You have to understand like that. It is not exactly like that. You have to understand like that. For remembering the concept, you have to understand it like that. So these things are very important. You have to write these two definitions about the position and about the polarity while writing these things in your exam paper. Okay. So hope these things are very clear, and I hope you enjoyed this video. We'll meet in the next class. Thank you.